What is time? A deceptively simple question, yet it is the key to understanding relativity. It is also the reason my hair is going gray. When we describe motion, we do so as a function of time. 10 meters per second, 100 miles per hour. But the mathematical description of velocity is moot, unless we can define time. Is time universal? In other words, is there an audible tick-tock throughout the galaxy? A master clock, so to speak, forging ahead like Mozart's metronome? The answer, my friends, is no. Time is not absolute. In fact, for us believing physicists, the distinction between the past, present, and future is but a stubborn illusion.
Okay, so it's all about time travel. So it's an investigation. While we're investigating the possibility of time travel, you will get to learn quite a bit about modern physics. That's the whole idea. It's an investigation, but it's a good way to learn modern physics. The first condition that needs to be satisfied for time travel to be possible is the time needs to be continuous, which means that the past, the future, the present all need to happen at the same time. And according to Einstein, they all happen at the same time. It says the difference between the past, the present, and the future is all about an illusion, about a persistent one. All right, so we got a bunch of questions. If everything happens at the same time, why is it that we only perceive the present, not the past and not the future? If the future, the past, the present all happen at the same time, can we go to the future? Can we take shortcuts to the future? Can we go to the past? Can we take shortcuts to the past? So that becomes an investigation. And we will follow through. All right, so 4 questions. And you will get them all wrong, believe it or not, because the only thing you got going for you is common sense. No one gets these questions right. The first question is the one that we've been on for ever since the beginning of this semester. Imagine that you're traveling at the light speed with a mirror in your hand. And if you were to look into the mirror, would you see your reflection in the mirror? Common sense will say no. Why not? Because look, you're traveling at the light speed. Your face is traveling at the light speed. The mirror that you're holding is traveling at the light speed. Light from your face to the mirror is traveling at the light speed. Everything is moving in the same direction at the same speed. There's no way. There's absolutely no way that the light from your face is going to reach the mirror, because both of them are moving at the same speed in the same direction. We'll say the common sense. Einstein will say nonsense. Light from your face will reach the mirror, he will say. So the question is how? Is time traveling to the future possible? Answer to that question is yes, of course, 1 second at a time. That's not what I'm talking about. Can you leap 100 years into the future within a fraction of a second? 1,000 years into the future, 1,000,000 years into the future, within a fraction of a second, without resorting to wormholes? No science fiction. Common sense will say absolutely not. Einstein will say absolutely yes. So the next question is, how's that possible? This one is the one that's going to make sense. All right, this one is the hook. At this point, I'm fishing around, and this is going to hook you on immediately. Imagine that we're capable of traveling at the light speed. We've got this spacecraft that allows you to go at the light speed from here to New York City at the light speed. How much of the landscape do you think you're going to be able to see if you're traveling at the light speed when you look outside? The entire trip is going to take a fraction of a fraction of a fraction of a second. What would you see within a fraction of a second, if anything? Nothing. You see absolutely nothing in a fraction of a second. It will not register. All right, nothing is going to register in your brain. Nothing. So the entire trip is going to take you a fraction of a fraction of a fraction of a second. So what do you see? Nothing. In all appearance, the space is going to look shrunken to a point. The landscape of Chicago is going to turn into the landscape of New York City within a fraction of a second. It's a magic trick. So space is going to look up here contracted in the direction of motion. That's the only one. That's the only one. Your mind goes, okay, I get it. I get it. And you're not going to comprehend it because you're thinking, oh, it's something to do with your perception. Actually, it doesn't. It seems like it does, but it's not. In the last statement, is it possible for any mass to travel at the light speed, but faster? Your mind is going to say, why not? I mean, you kind of understand that it's probably impossible today, but it's just a matter of technology. Like one day, what we cannot do today will be done. It's going to be doable. 70 years ago, we cannot travel at the speed of sound. Today, we can. Traveling at supersonic speeds is nothing today. We got the technology. So you're thinking it's a matter of technology, and Einstein will say absolutely not. It's got nothing to do with technology. It simply cannot be done. Nothing with mass, Einstein will say, can travel at the light speed or faster. It's something weird happens. Year is 2011. And that physicist announced that particles called neutrinos were traveling faster than light. Einstein said nothing can travel faster than light, and these particles appear to be traveling faster than light. The problem happened with neutrinos. They're almost massless, but they do have masses, but they are just so incredibly light that we did not know exactly what their masses were. So in trying to figure out the masses of these particles, physicists were conducting experiments. Over at CERN, Switzerland, only realized that these particles were actually traveling faster than light. There was this excitement and uproar in the physics community. Well, I liked more like excitement and uproar in the press. Physics community, I was at Fermi Lab at the time, remained unmoved by this announcement. We were skeptical. These people repeated this experiment, God knows how many times. Roughly about 1,000 people working on this project, which is known as the UPRO project, trying to figure out the mass of the neutrinos, discovered that the neutrinos were traveling faster than light. So the question became, did Einstein get it wrong? Or is it possible that about 1,000 PhDs end up messing up the experiment maybe about 20,000 times?
Interesting. Coca-Cola or Pepsi-Cola. A paradox. While molecularly similar, they logically seem to offer two possibilities. Of course, you must invariably arrive at one and only one correct choice.
Yeah, I mean, the correct choice is Coke, right? Coke is definitely better than Pepsi. And those of you guys who like Coke better than Pepsi, give yourselves 5 points. Those of you guys who like Pepsi better, I got news for you. Your presence in this Zoom meeting is offensive to me. I mean, you got Coke. Why would you like Pepsi over it?
A no-brainer.
Damn, Einstein, you picked the wrong one again. Coke versus Pepsi, which one is better? It's relative, right? So those of you guys who like Pepsi, give yourselves 5 points as well. There's no such thing as the right answer when it comes to taste. Taste is not relative. People like different things. Guess what, guys? Evidently, the way we experience time and space is also relative. This is known as Einstein's theory of relativity. This theory is going to make time travel possible. The theory was first published in 1905. It's called special theory of relativity. It's special in the sense that the special is used in the politically correct terminology. Special means limited. All right, it's a specialized theory of relativity. That's probably more correct assessment of it. It's special or limited to the case of motion near the light speed, the constant velocity. So which means that as long as you're moving a straight line at constant speed near the light speed, everything that we will discuss is going to be correct. All right, so you need to be moving very near the light speed. You cannot speed up, you cannot slow down, and you cannot change direction. So under these special conditions, everything that we will discuss is not correct. Something is going to happen to motion. Remember the meaning of motion, the way we defined it in physics 1. Motion is the displacement of mass in space and in time. So near the light speed at a constant velocity, something is going to happen to your mass, something is going to happen to your time, and something is definitely going to happen to space. All right, so these are the topics of discussion for this week. Everything goes back to Einstein when he was 16. Had a mind twister, a what if question. What if you said I'm traveling at the light speed with a mirror in my hand? Would I be able to see my reflection inside the mirror? Well, it depends. If the light from your nose reaches the mirror and gets reflected back, of course you will be able to see the reflection of your nose. There's your nose hair, is the reflection of the nose hair. This is fine. But if you're traveling at the light speed, and if the mirror is also traveling at the light speed, will the light from your face ever get to reach the mirror? So that becomes the question.
Imagine if I'm sitting still and holding a mirror to my face. And the light travels from my face to the mirror, and I see my face.
Yes.
However, if I and the mirror were traveling at the speed of light...
You're going at the same speed as the light leaving your face.
Exactly.
The light never reaches the mirror.
So would I be invisible?
That doesn't make sense.
Young Einstein was starting to realize that light was unlike any other kind of wave. Einstein was about to enter a surreal universe where energy, mass, and the speed of light intermingled in a way no one had ever suspected.
All right, so there are a couple of ways of looking at this question. There are 2 ways of looking at it, and 2 different ways, 2 different approaches to this question, and both of them will give you answers, but the answers will contradict. Here's Einstein's face, the mustache. Here's light moving away from him at the light speed. Here's the mirror moving at the light speed. So this is Einstein moving at the light speed. The light is moving at the light speed. The mirror is moving at the light speed. Will this light ever reach the mirror? All right, so everything is moving in the forward direction at the light speed. Will the light ever reach the mirror? Well, it's an easy question to answer. Imagine that somebody tries to run me over with a car. I barely escaped with my life. What am I thinking? I'm thinking revenge. All right, so I grab a rock, try to smash the back window, right? Except the problem is the car is going at 60 miles per hour. The fastest I can throw this rock is also 60. Will this rock ever reach the car? You know the answer, right? No. I'll go through the motions. It's never going to reach the car because for it to be able to reach the car, it needs to move faster. Okay, so we got the same problem here. The mirror is moving at the light speed. The light is moving at the light speed. Will this light ever reach the mirror? Nope, nope. All right, so these two scenarios are identical. So one answer says absolutely not. You won't be able to see your reflection. So that's a straightforward answer. Okay, so let's change the scenario this time. Just place Einstein inside some kind of a spacecraft capable of traveling at the light speed. We place the mirror right on the wall. So the spacecraft is moving at the light speed. Einstein is inside the spacecraft. The spacecraft is moving at the light speed as well. So will this light ever reach the mirror if that's the case inside this reference frame of reference? Okay, now let's come up with an answer. Imagine that I'm inside a bus. The bus is traveling at 60 miles per hour. I got a baseball in my hand. I'm capable of throwing the baseball at 60 miles per hour. So I throw the baseball in the forward direction at 60 miles per hour. So how fast will it be moving relative to me when I throw the ball at 60 miles per hour? You know, if this is the fastest I can throw, it's going to be moving at 60 miles per hour relative to me, right? Relative to everyone on the bus. I'm on the bus, everyone else is on the bus. So relative to me, this baseball is going to be traveling at 60 miles per hour because that's the fastest that I can throw this baseball. So what if the bus is moving at 120 miles per hour? How fast is the baseball moving relative to me? Once again, it's going to be moving at 60 miles per hour because, you know, that's the fastest that I can throw. So it's independent of the motion of the bus. So what if this is an airplane now traveling at 450 miles per hour? Let's just... Okay, so how fast do you think it's going to be moving if that's the case? If it's moving at 450 miles per hour, it's still going to be moving at 60 miles per hour relative to me because this is the fastest I can throw this, right? So what if I'm inside a spacecraft moving at half the light speed? I throw this in the forward direction. How fast is it moving relative to me? It's still 60 miles per hour. What if this thing is moving at the light speed, this spacecraft right now? I throw the baseball in the forward direction at 60 miles per hour. How fast is it moving relative to me? Once again, it's going to be 60 miles per hour. So how fast the baseball moves is independent of the motion of my reference frame. It doesn't matter that it's moving at 60 miles per hour, 100 miles per hour, 500 miles per hour, after light speed, at the light speed, it makes no difference. Likewise, just go into the bathroom. There's a mirror. Check yourself out at the mirror. All right, so how fast do you think that the light is moving towards the mirror from your face? Light speed. You will see yourself in the mirror as soon as you look at it. There's no delayed reaction. You're driving at 60 miles per hour. You check yourself out in the mirror. How fast does it? How long before you see yourself? It's immediate. All right, the light still moves at the light speed relative to you, regardless of how fast you may be driving. On an airplane, it's moving at 550 miles per hour. You look into the mirror. Do you see yourself immediately? Answer that question. Of course you do, right? How fast do you think the light is moving relative to you? Once again, it's moving at the light speed relative to you, independent of the motion of the reference frame that you're in. Likewise, if you're inside some kind of a spacecraft traveling at half the light speed, if there's a reflective surface, you should be able to see your reflection immediately. Once again, the light is going to be traveling at that light speed relative to you. Even if your spacecraft is moving at the light speed, you should still be able to see your reflection because light still moves at the light speed relative to you. All right, the same argument. Notice that the physics gives you two contradictory answers for the same question. So the question becomes, which one is the right answer? Okay, under the circumstances, normally the thing to do is we take the simplest answer. All right, the simplest answer is you're not going to be able to see your reflection. That's it. What's wrong with this answer? Here is what's wrong with this answer, guys. Let's go along with Einstein's finding. According to Einstein, Einstein will say you should be able to see your reflection in the mirror because relative to you, the light is always going to travel at the light speed. So regardless of your motion, light always travels at the light speed relative to you. All right, let's go with that conclusion. So let's say that the light moves at the light speed with respect to you, regardless of your motion. So relative to you, light moves at the light speed. All right, you're moving at the light speed. Light moves at the light speed relative to you. You're not moving at all. You're stationary. Light still moves at the light speed relative to you. All right, so let's go along with this conclusion. What's the worst that can happen if this conclusion is correct? Let's take a look. Let's have a station observer, someone outside, watching this ball go by inside this bus. All right, so this person is looking at this ball. Imagine that this bus is transparent so he can see the ball. So the ball is moving at 60 miles per hour relative to the bus. Bus is moving at 60 miles per hour relative to him, so which means that this ball is moving at 120 miles per hour relative to this guy. All right, so the only thing I did was I added the speeds. Ball at 60 miles per hour relative to the bus at 60 miles per hour relative to this guy. So which means that this ball is moving at 120 miles per hour relative to this outside stationary guy. That's it. The only thing we have to do was just add up the speeds. So this guy is going to see the ball moving at 120 miles per hour. Now he's looking at the light in Einstein's reference frame. So Einstein's reference frame is moving at the light speed relative to him. And within the reference frame, the light is moving at the light speed relative to this reference frame. So which means that this light should be moving at double the light speed relative to the stationary observer. Yeah, but all of a sudden this is in contradiction to the statement. Okay, light should be moving at the light speed relative to everyone, regardless of their motion. Light should be moving at the light speed relative to Einstein. Same light should be moving at the light speed relative to the stationary observer. This classical logic ended up breaking down completely. Everything just went to hell in the handbasket. So out of these two possible conclusions, the first one is straightforward. This didn't go anywhere. At that point, most of us would just give up and say, well, you know, this obviously out of two conclusions, you say light won't be able to reach the mirror, so you won't be able to see your reflection. Einstein is not like that. He decided to take the opposite view. He came up with two postulates. Postulate number one is called relativity postulate. Relativity postulate is exactly what I said initially, which is the special conditions within which everything that we will discuss is going to be correct. So relativity postulate means we're going to be moving at a straight line at constant speed without speeding up or slowing down, and you will be moving only near the light speed. And according to postulate number two, the light is going to move at the light speed relative to you, regardless of your motion. That's it. So the thing to focus on right here is, let's not make it complicated. Let's focus on the meaning of postulate. What is a postulate? Because Einstein is a very postulate-happy person. So what's the meaning of a postulate? If somebody is postulating, does this mean that the person is constipated? All right, so what is it that you guys visualize when somebody says postulate? Now, this term is important. Postulate simply means it's an assumption. I hate to say it, guys. I hate to say this. It's an assumption. Einstein is saying, I'm going to build up a theory based upon these two assumptions. But it's not saying assumptions. He's saying postulates. Because when you say let's assume, somebody says let's not. But when somebody says let's postulate, you go, wow, that sounds really, really, really powerful. Because the term postulate has gravitas. All of a sudden, it gets your attention. And now it's got some importance. Newton is very happy with his laws. He comes up with these theories and calls them laws, and Einstein calls everything postulate. He's building a theory based upon assumptions. The theory has two assumptions. Assumption number one, first postulate. You're moving in a straight line at a constant speed near the light speed. No speeding up, no slowing down, no change in direction. And the assumption number two is light, regardless of your motion, will always move at the light speed relative to you. So what does it mean? Which means that even if you're traveling at the light speed, you should be able to see your reflection in the mirror. That's what it means. What that means is if I'm driving my Super 4 Tempo at the light speed, if I were to turn on the headlights, I should still be able to see what's in front of my vehicle. That's what it means. Got it? It's an assumption. Don't confuse assumptions with science. Anyone can pull a postulate out of their buttholes. All right. The only thing you have to do is instead of saying let's assume, you say let's postulate. So Einstein says, I'm going to make the assumption that you will get to see your reflection in the mirror, even if you're traveling at the light speed. So the question becomes, what gives? All right, so you got two spaceships traveling at half the light speed. And both of them, one of them is moving directly towards the sun, the other one is moving away from the sun. All right, so both of them are moving at half the light speed. While they're trying to measure the speed of light, what do they measure for the light speed? Both will measure the same speed for light. Why? Because in every single reference frame, regardless of their motions, according to Einstein's postulate, light still has to travel at the light speed. Speed of light is independent of the motion of your reference frame. That's what it means. So the best answer is going to be D. D is going to be the best answer for them. All right, so the question becomes what gives? Imagine that your speed, this is V, approaching the light speed, which is C. You know the speed is measured distance over measured time, right? All right, so when you take the distance and measure it by time, it should give you the light speed if you're traveling at the light speed. So the question becomes, what happens to space in the direction of motion at the light speed? What happens to space? It shrinks to a point. All right, so when you take space and divide it by time, you should still get the light speed. So if the space tends towards zero, the time is also going to tend towards zero, which means that this time is going to slow down. So the space is going to contract in the direction of motion, which is known as the contraction of space. Time is going to slow down, which is known as the dilation of time. So these are the conclusions. These are the predictions. So two predictions. When you start to approach the light speed, the space is going to contract in the direction of motion, and the time is going to slow down.
Hold on. We're taking off.
Fortunately, this phenomenon is only noticeable close to the speed of light. Imagine yourself alongside early 20th century science fiction swashbuckler Flash Gordon. When not fighting the bad guys, or trying to escape from some monster, you're dashing around the galaxy at incredible speeds. While you are, your clock and those back on Earth are running at different speeds. Assuming you've been gone for the better part of a year, when you get back, everyone you knew would have been dead thousands of years. It's the ultimate example of relative time.
All right, so faster you go, if you're traveling at a higher fraction of the light speed, the more the time is going to slow down. What that means is faster you travel, the slower the time becomes. All right, so closer you get to the light speed, the slower your time is going to tick.
8, 7, we are go for it. Start 5, 4, 3, 2, 1. Booster ignition and liftoff of Atlantis on a mission to study planet Earth.
Astronauts travel 30 times faster than corporate jet pilots. Joe Tanner traveled 4.5 million miles when he flew in a shuttle mission in 1994. Joe has an identical twin brother, David.
After the spaceflight, now I am 321 microseconds younger than I was before the spaceflight. I guess I don't feel all that much different. Well, I used to have a mustache like yours, but everyone says I look so much younger without it. I shaved it off so I could catch up on those 321 microseconds.
Joe and David are now living examples of what physicists call the twin paradox, a result of time dilation. The question of why time slows down for one traveler as he approaches the speed of light, but not for the twin who stayed behind. As fast as the shuttle is going in orbit, it's only going a tiny fraction of the speed of light. That's why Joe is only 321 microseconds younger. Again, it's a problem of human perception. Joe and David and the rest of us have only experienced a tiny slice of time and space. Beyond our realm of the senses, our Umwelt, things move incredibly faster and incredibly slower.
8 seconds younger. I guess I don't feel all that seconds younger than I was before the spaceflight. I guess I don't feel all that much different. Well, I used to have a mustache like yours, but everyone says I look so much younger without it. I shaved it off so I could catch up on those 321 microseconds.
Joe and David are now living examples.
Okay, 321 microseconds. What is a microsecond? It's a millionth of a second. It's a millionth of a second. How do they even measure a time difference in terms of millionth of a second? Atomic clocks. All right, so they had two atomic clocks synchronized initially. You place one of them inside the space shuttle, send it out into space, let it orbit the Earth for about a week or two. Upon return, check to see if they're still synchronized. Obviously, they're not. One of them is slightly slower. The one from space is going to be 321 microseconds slower. That's the evidence. So how does that prove Einstein's theory right? Well, it proves Einstein's theory right because this formula will give you the same answer in terms of the difference in time. I noticed that we got two times. One of them is t, the other one is TO. TO represents the original time or the proper time. T represents relativistic time. All right, so TO, the proper time, is getting measured by a person or an instrument traveling near the light speed or relativistic speed. All right, so this is the time which is going to be measured by the reference frame, within the reference frame, traveling near the light speed. And T, relativistic time, is the time that we measure for that particular event here on Earth. So the proper time measured near the light speed, and relativistic time is the time measured here on Earth. That's what it is. V represents your speed relative to the light speed. So you should be moving near large fraction of the light speed for the time dilation to occur. So there's going to be a difference in time between the time that we measure here on Earth and the time is originally measured in the reference frame traveling near the light speed. All right, so how does that work? It's important. We got one twin traveling at 17,500 miles per hour. That's the orbital speed around the Earth. It's a very small fraction of the light speed. All right, so this is 17,500 miles per hour. It's the smallest small fraction of the light speed. Imagine that this twin astronaut spends about 10 years in space. Upon return, what is he? Nothing. He's going to be 10 years older. His twin is going to be 10 years older. The time difference is probably, at most, it's going to be a second. I doubt it. That's within 10 years. I don't think it's going to be a second. All right, so both of them are going to be 10 years older. What if the twin in space is traveling at 90% of the light speed? travels 10 years in space, and then upon return, he discovers that within the 10 years that he's spending in space, it's going to be about 23 years here on Earth. His twin is going to be 13 years older, the one who stays here on Earth. What if this twin was traveling at 95% of the light speed, 10 years in space? What would he discover? He would discover that it would be about 32 years here on Earth. His twin will be about 22 years old. At 99% of the light speed, the guy spending 10 years in space would discover that it would be 71 years here on Earth. All right, I doubt it that his twin would be alive. At 99.9% of the speed of light, within 10 years, he would leap 223 years into the future. At 99.999% of the speed of light, within 10 years, he would leap about 700 years into the future. At 99.999% of the light speed, within 10 years, he would leap about 2,200 years into the future. Guys, imagine having this technology of being able to travel at this speed 2,200 years ago. If you miss the main event, you will be arriving just about now to catch a movie version of it. I'm talking about crucifixion. From what I understand, the movie version is just as gruesome and just as nasty, just as disgusting. Except it's a lot more fun to watch because of the background music. Notice that closer you get to the light speed, the deeper into the future you can lead within 10 years. All right, so closer you get to the light speed, the more your time is going to slow down, and deeper into the future. That allows you to be able to jump. All right, so the twin on Earth will predict that the astronaut twin is going to be universe, but he's the best astronaut. Okay, so I don't know how many of you guys seen the movie Interstellar. I saw the movie and I evidently misinterpreted some of the facts regarding that movie. And I kind of like my misinterpretation regarding that movie. Okay, if I can predict our future, human population is growing fairly fast. Planet is not going to be able to support this sort of growth. And I can almost predict that within the next 100 years, we're going to start to run out of resources. In the 1970s, the world population was about 4 billion. Right now, it's 7 billion, almost 8 billion. Eventually, we will run out of resources. And then the humankind may not be able to survive this ordeal within more than 100, maybe about 200 years. Okay, we cannot keep expanding like that. Unless we can colonize the universe, all right, we're going to end up self-destructing at some point. Okay, now having said that, if we wanted to colonize the universe, we need Earth-like planets. And we've been looking for Earth-like planets. I don't know, 7, 8 years ago, we found a planet located roughly about 800 light years away. And they named it the Super Earth. The reason why they call that, because it's supersized. And it's supposed to be like Earth in a lot of ways. And so the question is, how long would it take for us to get there if we wanted to colonize? So imagine that we have the capability of traveling at the light speed, which we don't. All right, how many people will even volunteer to just go to a planet which is 800 light years away? Even if you volunteer, would you even get there? Would you even be able to see it while traveling at the light speed? Okay, now notice what you guys are thinking. You're thinking that no, it's not doable. All right, because you're not going to live 800 years, which means that even if you're traveling at the light speed, it would take 800 years for you to get there. 800 years. You know, you won't be able to see anything within that 800 years, right? So would it worth your life to actually travel there? And obviously, for you to be able to, you won't be able to get there in your imagination, but you know, you can procreate. So I don't know, maybe 20 generations later, someone from your genetic side is going to be able to arrive there and populate the planet. Well, if that's what you were thinking, you're missing the point. What is it that you're missing? Here's what you guys are missing. What happens to the time if you're traveling near the light speed? It slows down, right? What do you think is going to happen to the time if you're traveling at the light speed? It stops, guys. It stops. Time stops at the light speed. If you're traveling at the light speed, it takes you no time to get to the planet 800 light years away. It takes no time at all. All right, so you're here traveling at the light speed. You're there. It takes no time at all. You look around, there are creatures who look like fish. Guess what? You don't like fish. You don't want to live there. And then you turn around, you come back home. How long is that going to take? It's going to take absolutely no time at all. From your reference frame, from your perspective, you're there, now you're here. Except from our perspective, your entire round trip took 1,600 years, which means that you will arrive 1,600 years in the future. Now you look around, you notice that thanks to evolution, people here look like fish. Now you can never go back home. All right, you can only leap forwards in time.
60-second adventures in thought. Number 5. The twin paradox. Albert Einstein didn't have a twin brother, but he had some funny ideas of what you could do with one. He imagined two identical twins. Let's call them Al and Bert. Now, Al is a couch potato, but Bert likes to travel. So he hops into a spaceship and zooms off at close to the speed of light. That's when Einstein's special theory of relativity kicks in. It says that the faster you travel through space, the slower you move through time. So from Al's point of view, Bert's time would be moving slower than his own. To put it another way, time might fly when you're having fun, but when clocks fly, they run more slowly in relativity. After a while, Bert decides to head back, still at close to the speed of light, and returns to his brother with his holiday snaps. But when Bert arrives home, Al will now be older than his twin, which makes their double date a lot more awkward. Although it seemed implausible, Einstein just followed his theory to its logical conclusion, and it turned out he was right. This concept of time dilation provides the basis for our global positioning system, which is how your sat-nav knows you need to turn left in 200 yards.
All right, so here's a question for you. Where's the paradox? I don't see any paradoxes from the way they described it. The paradox means you have to have two contradictory conclusions. There's only one conclusion here. The one who's traveling near the light speed is aging less. That's it. All right, so the question becomes, which one is traveling near the light speed? Guys, speed is relative. All right, so when I'm traveling at 60 miles per hour, I'm traveling 60 miles per hour relative to the Earth reference frame, relative to the surface of the Earth. While the surface of the Earth is also spinning on its axis about 1,000 miles per hour. The Earth is not stationary in space and spinning like it's spinning top. It's also moving relative to the sun, 60 to 70,000 miles per hour. The sun is not stationary. It's moving relative to the center of the galaxy. The center of the galaxy is not stationary. It's moving relative to other galaxies. Everything is in motion. All right, so speed. If you have two objects moving at a constant speed in a straight line, if you got no windows or whatever, it's called an inertial reference frame because at that point you cannot tell whether you're moving or not. Everything is going to feel stationary. So the question becomes, who's moving with respect to whom near the light speed? All right, is it the twin astronaut in space moving at 90% of the light speed relative to the Earthbound twin? Because from his perspective, he's not moving at all. It's the Earth which is moving at 90% of the light speed relative to him. All right, so from our perspective, he's moving at 90% of the light speed relative to us. From his perspective, we're the ones. We're moving at 90% of the light speed relative to him. So the question becomes, who's going to age less? All right, so this is the reason why it's known as a paradox. The answer to that question is straightforward. You know, both of them were at the same place at some point, right? So one of them had to accelerate to speed near the light speed. And then that one also had to decelerate so that he would come back here on Earth. While he was coming back to Earth, it was just slowing down. That's what it means. So the one that experiences acceleration and deceleration is the one that was moving near the light speed relative to the one here on Earth. So that becomes the resolution of the twin paradox. Okay, so when you're traveling near the light speed, your time is going to slow down, right? We kind of established that. But would you notice that your time is slowing down? I mean, do you look at the clock and say, oh, you know what, my 1 second started to take a lot longer than I was anticipating. We must be moving very near the light speed. The answer to that question is no. All right, that's the weird thing about relativity. In your reference frame, it doesn't matter how fast you're moving. Everything is going to look and feel the same. Your 1 second is still going to take 1 second long. Everything inside is going to look the same while you're moving near the light speed. But if we're watching it live on TV, then the things are going to look different to us. Imagine that you're inside this spaceship, which is moving near the light speed, starts to move near the light speed. When you start to gain speed, when you start to accelerate, and when your speed starts to become large fractions of the light speed, your 1 second is going to be a minute long in our reference frame, and that's going to be an hour long, it's going to be a day long, it's going to be a year long, it's going to be 100 years long. We will watch you slow down to a stop, and then you will start to look frozen. So from your reference frame, everything is going to look fine. From our reference frame of watching you live on TV.
At any given second.
This is what we will see.
In here, it's always Friday.
This is what you will experience from your reference frame. From our reference frame.
Boom, 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 boom. How.
What is this bizarre structure in the middle of the French countryside? And why was it abandoned? The surprising answer stems from the sea trade between the
All right, so every single aspect of Einstein's theory of relativity has been tested and tested and tested like a billion times. Okay, when I say a billion times, it feels like a bit of a slight bit of exaggeration. It's not, guys. When I say a billion times, it's probably more like a trillion times, if not more than that. Every time you run a particle physics experiment, it's a demonstration of Einstein's theory of relativity in essence. So every single aspect has been tested and tested and tested to be accurate. Einstein's theory of relativity is a theory by name only. It's a scientific fact.
But you got things you have to do now, and so do I. And so, I'm gonna get on this spaceship. And I'm gonna go to Blargon 7 in search of alternative fuels. But when I return, 200 years from now, you'll be long gone. But I won't have aged at all. So you tell your great-great-granddaughter to look me up. Because Adrian, baby, I'm gonna want to meet her.
Joey from so time is going to slow down. Space is going to contract. It's going to contract into directional motion, and it's going to contract into directional motion outside of your reference frame. This is in our project. I had done myself. This is like 20 years ago. I was taking a Photoshop course over at COD, the College of DuPage, just for the hell of it. Took the picture when I was living in New York City. And then I did some artsy stuff to it using Photoshop, trying to demonstrate what you would experience if you were traveling at half the light speed. This is half the light speed from left to right. So you're moving in this direction. If you were to look outside, you would see the contraction of space. The space that you leave behind is going to look reddish. The space that you're moving towards is going to look bluish. Obviously, the picture was taken before 9/11, so you see these Twin Towers in the background. You would see the contraction of space only if you're looking outside. On the inside, everything would look the same. Your time would slow down, but you wouldn't notice it, obviously. All right, so this is known as the contraction of space in the direction of motion. So the question becomes, is it possible for anything to travel at the light speed? What happens to mass? All right, so what prevents us to travel at the light speed or faster? All right, so according to Einstein, what's going to happen is when you start to approach the light speed, you become more and more massive. All right, so the energy that you put in order to reach the light speed is going to go into your mass. All right, so closer you get to the light speed, the more massive you will become, in essence. So what happens if you're traveling at the light speed? So your speed becomes the light speed. So C divided by C is going to be 1. 1 minus 1 is going to be 0. And this is your mass. In my case, it's 150 pounds. If you take your mass and divide it by 0, it's going to give you infinity. So I would become infinitely massive. So that's what would happen. So the amount of energy required for any mass to travel at the light speed, we will become infinitely massive. So what's wrong with that? Well, the problem with that is the faster you go, the more massive you will become. And then obviously, the closer you get to the light speed, the more massive you will become. And very near the light speed, my 150-pound mass is going to become over, it'll be over.
Ken, your sound just started distorting.
All right, let's fix that. Is it better?
Yes. Yeah.
All right, so when you start to approach the light speed, you go up 5 points. The mass is going to increase, right? That's what it means. So once again, the question is, so what? Why can't anything with mass? Why can't anything with mass travel at the light speed? What prevents it? What prevents us to travel at the light speed? Well, the problem is this, guys. Your mass is going to become infinitely large. So what's the amount of energy required for you to be able to travel at the light speed? All right, so if you're infinitely massive, what's the amount of energy required for you to travel at the light speed? So this is the formula, it gives you the answer. So you need infinite amount of energy for any mass to travel at the light speed. That's what it means. The problem with that is the universe is finite in size. How do we know that? Because it started from a point, a Big Bang. So, which means that the energy in the universe is also finite in size. We don't have infinite amount of energy in the universe. All right, we have finite amount of energy in the universe. So, which means that we will not have enough energy for any mass to travel at the light speed or faster. That's the meaning of it. So there's no way anything with mass can travel at the light speed. All right, so this is a relativistic constant, something we will discuss in the next lecture. So don't worry about it, just get the concepts right now. So for any mass to travel at the light speed, the amount of energy required would be infinitely large. The universe is finite in size. The amount of energy in the universe is also finite, so we don't have enough energy in the universe for any mass to travel at the light speed or faster. All right, so here's the reason why nothing in the universe, nothing with mass in the universe can travel at the light speed or faster. All right, so that's the statement.
This fall, physicists in Italy published results suggesting that neutrinos travel faster than light.
Yeah, so what about the neutrinos? Did Einstein make a mistake?
Significantly faster. If true, this is really big news in physics. And of course, most scientists are greeting the results with skepticism. Why, you might ask? Well, they fly in the face of the well-established and experimentally supported theories of special and general relativity. And extraordinary claims require extraordinary proof. So let's go visit the opera experiment in Italy and try to catch some neutrinos. The kind researchers looking for the Higgs boson at the LHC in Switzerland are already crashing protons into each other to create explosions of subatomic particles. And luckily, some of those particles are neutrinos, which fly straight through the Earth's crust to us here in Italy. There are just 3 things that we have to do. 1, we have to catch the neutrinos, which, given that neutrinos will travel for roughly 2 years through lead before stopping, is an ambitious task. But we can do it. 2, once we have a neutrino, we have to figure out which proton collision it came from. Imagine blowing up a case of wine bottles at night, and then having your neighbor call you up and say, "I got a piece of glass. Can you tell me which one it is?" Well, we're that neighbor. And 3, once we figure out which collision the neutrino came from, we have to know exactly what time the collision happened, and exactly when we caught the corresponding neutrino. And because the scientists in Switzerland are hundreds of kilometers away, we have to use timing signals from GPS satellites in order to synchronize our clocks. If we're off by even a microsecond, we'll get the speed wrong by 1,000,000 kilometers per hour. So that's it. Now that we've measured the neutrinos going faster than light, what next? Well, because our results are so groundbreaking, and our observations so hard to make, the scientific community wants to be absolutely sure we didn't make any big mistake. So we have to wait for other experiments around the world to confirm or refute our claim. And this could take months, or even years, so be patient. And in the meanwhile, why not learn more about neutrinos, or how GPS works? Click below to make a choice.
Well, they almost got it right, for the most part. So they discovered that the neutrinos were traveling faster than light. There was a huge uproar in the press. Physics community in general remains skeptical. Why, you say? Well, I explained the reason why. Because the amount of energy required for anything with mass, to travel at the light speed, the infinite amount of energy is required. One thing about neutrinos we knew, they got masses. They do have mass. All right, the question was, what is that mass? So that's what they were trying to figure out. And next thing you know, they discovered that the neutrinos were traveling faster, and they skipped the peer review and they went to press, in essence. So this was a big no-no. In reality, what needs to happen is there's a peer review, and then you repeat the experiments. Experiments need to be verified by other independent researchers. And then once the verification is in place, at that point, you can just publish it and get credit for it. They just got so excited, they decided to skip the peer review. And then obviously they repeat the experiment, I don't know how many times, thousands upon times. And then they came up with the same results. And then the second set of physicists came in. All right, so the first set of physicists vacated. That's the only the place where you could run this experiment. And then when the new set of physicists came in, for example, I'm a computational physicist, I would check to see if the programs are working properly. You got experimentalists, they would check the instrumentation, this and that. And then they discovered a loose cable somewhere. They tightened it up. And next thing you know, the neutrinos began behaving themselves. This is so happens, they were not traveling faster than light. It's just an experimental error, instrumentation. That was the extent of it. A bunch of physicists were forced to resign, in essence, end up losing their jobs.
This, we found an anomaly. We found that the speed is not what we would expect, namely very close to the speed of light. But it seems to be a little higher, 20 parts per million. You could say it's peanuts, but it's not. It's something.
It was significant, obviously, enough to claim that they were traveling faster. And then it just so happens there was an instrumentation error. People end up quitting or forced to resign. It's kind of sad. I don't know. There are probably 1,000 people working on this research. And then they were able to get themselves fooled. What's the problem with what they came up with? Number one, guys, anything with mass cannot travel at the light speed or faster. How do we know that? It's just not simply that little derivation that I did. Einstein's theory has been tested. It's just like a trillion times. Every time we do a particle physics experiment, within those experiments, you have particles, trillions upon trillions upon trillions upon particles moving near the light speed, and none of them can and will move faster than light. All right, the lightest particle you can imagine is an electron. We cannot get an electron to move at the light speed. It's out of the question. Another way of looking at it is what would happen to time from our perspective. Okay, what happens to time when you start to move near the light speed? It slows down. What happens to time at the light speed? It stops. I mean, deep down, I was hoping that Einstein would be wrong, knowing full well that he wasn't. What would happen if you were to exceed the light speed? You're coming very close to the light speed, the time slows down. At the light speed, stops. Exceed the light speed, time reverses itself. So what is that supposed to mean? What that means is, if it was possible for anything to travel faster than light, especially particles, AT&T would be able to offer us extra services for an extra fee so that we could communicate with ourselves in the past. That's what it means. If you're like me 50% of the time, you're screwing things up. it would be nice to be able to hear from my future self and say, hey, listen, you're going to make a decision today and make that decision instead of this decision. If we had particles traveling faster than light, backwards in time communication would be possible. And guess who got that? This cartoonist did. I cannot believe it. 1,000 physicists missed the point, and yet this guy got it. It's called the Neutrino news. And this guy published it. He's talking about the results of today's faster than light experiment. He's talking about that they're coming through now. He says, hang on, these are the results of the next week's experiment. Yes, which means that if things are traveling faster than light, all right, backwards in time communication would become possible. You could call yourself up and talk to your past self. The communication would be only one way. You can just call yourself up and leave a message. You could not hear anything from the past, but you can definitely talk to the past. It's not possible.
Since near the velocity of light, we cannot simply add speeds. The familiar notions of absolute space and absolute time, independent of your relative motion, must give way. That's why, as Einstein showed, funny things have to happen close to the speed of light. There, our conventional perspectives of space and time strangely change.
Your nose is just a little closer to me than your ears. Light reflected off your nose reaches me just an instant in time before your ears. But suppose I had a magic camera so that I could see your nose and your ears at precisely the same instant.
With such a camera, you could take some pretty interesting pictures. Paolo says goodbye to his little brother Vincenzo and rides off. He's now going more than half the speed of light. He's almost catching up with his own light waves. This compresses the light waves in front of him, and his image becomes blue. The shorter wavelength is what makes blue light waves blue. Also, Paolo becomes skinny in the direction of motion. This isn't just some optical illusion. It really happens when you travel near the speed of light. As he roars away, he leaves his own light waves stretched out behind him. Long light waves are red. We say that his receding image is red shifted. Now, Paolo leaves for a short tour of the countryside. He experiences something even stranger. Everything he can see is squeezed into a moving window just ahead of him. Blue shifted at the center, red shifted at the edges. To a passerby, Paolo appears blue shifted when approaching, red shifted when receding. But to him, the entire world is both coming and going at nearly the speed of light. Roadside houses and trees that he's already gone past still appear to him at the edge of his forward field of view, but distorted and red shifted. When he slows down, everything again looks normal. Only very close to the speed of light does the visible world get squeezed into a kind of tunnel. You would really see these distortions if you could travel near the speed of light. Someday, perhaps, interstellar navigators will take their bearings on stars behind them, whose images have all crowded together on the forward view screen. The most bizarre aspect of traveling near the speed of light is that time slows down. All clocks, mechanical and biological, tick more slowly near the speed of light. But stationary clocks tick at their usual rate. If we travel close to light speed, we age more slowly than those we left behind. Paolo's watch and his internal sense of time show that he's been gone from his friends for only a few minutes. But from their point of view, he has been away for many decades. His friends have grown up, moved on, and died. And his younger brother has been patiently waiting for him all this time. The two brothers experience the paradox of time dilation. They've encountered Einstein's special relativity. This was just a thought experiment, but atomic particles traveling near the speed of light do decay more slowly than stationary particles. As strange and counterintuitive as it seems, time dilation is a law of nature.
Who's this guy? This guy is Carl Sagan. This is Cosmos, the original show from 1970s. It's really, really well done. Carl Sagan was the first person who tried to popularize science, and he did a really good job. This was an amazing show, obviously. And also, Carl Sagan is the guy behind the movie Contact, the novel, the movie. All right, so more about Contact later. All right, so let's get back to the time travel aspect of it. Okay, so imagine that you find yourself near a black hole, and you're getting sucked into a black hole. All right, so you volunteer to get behind the event horizon, and then you just want to experience the reality of what takes place inside a black hole. And then we're watching you live on TV as you start to approach the black hole. Okay, so what are you gonna experience, and what are we gonna experience in terms of watching? What is it that we will see? Okay, so when you start to approach the event horizon, you're gonna speed up. The gravitational pull is gonna start to get larger and larger, and your speed is gonna start to approach the light speed. As we are watching you fall into a black hole, your 1 second is gonna be a minute long, And then it's going to be an hour long, it's going to be a day long, it's going to be a year long, it's going to be 100 years long, it's going to be 1 billion years long, which means that at some point you will become frozen in time. And that's it. Okay, and then eventually you're not going to move. Your 1 second is going to be infinitely long or something.
If you were watching an astronaut, foolhardy enough to jump into a black hole, at some time on his watch, say 12 o'clock, he would cross the event horizon and enter the black hole. But no matter how long you waited, you would never see the astronaut's watch reach 12 o'clock. Instead, each second on the watch would appear to take longer and longer, until the last second before midnight would take forever. Thus, by jumping into a black hole, one could ensure that one's image lasted forever. But the picture would fade very rapidly, and grow so dim, that no one could see it.
As somebody disappears into a black hole, as seen from the outside, it looks as though the time actually slows down, and the person becomes who's moving, at least he's thinking he's moving, he's perhaps talking in his spaceship at a normal rate, seems to slow down and ends up by being frozen in a particular position, as seen by somebody watching him from the outside. And as seen from the outside, you never see what happens after that.
The astronaut wouldn't notice anything special when his watch reached midnight, and he crossed the event horizon into the black hole. Until, of course, he approached the singularity and was crushed into spaghetti.
One can fall through this event horizon without feeling anything, without noticing it. After about a week of falling, one begins to feel the pinch and one extends longer and longer and gets slightly thinner. And, of course, one begins to get squeezed. Until one gets very long and very thin and rather nasty. By the end of 2 weeks, one's fallen right into the center and one is, of course, dead.
Before you lose sight of the outer world, you would see things happening, and you would see them at a greater rate, so that it would look like a firework display. The frustration would be that although you would be able to see everything that happens in the future, it would be going so fast that from a scientific point of view, you would have no time to analyze it. You wouldn't be able to take it in. And eventually, things would be going off so fast, and it would be so explosive that you yourself would be destroyed by the explosion, and that would be the end. But it would be a very exciting way to end one's life. It would be the way I would choose if I had the choice. Would be that although you would be able to see everything that happens in the future,
it's talking about seeing the future.
It would be going so fast that from a scientific
Okay, so you're falling into a black hole and you're seeing the future. How's that possible?
point of view, you would have no time to analyze it. You wouldn't be able to take it in. And eventually things would be going off so fast and it would be so explosive that you yourself would be destroyed by...
Okay, once you get past the event horizon, now things will become interesting. If we were watching you live on TV, your time is going to slow down. Your time is going to slow down. Because relative to us, you're moving at relativistic speeds. The closer you get to the light speed, the slower your time is going to become. But what if you are doing the same thing? What if you're watching us live on TV, trying to keep up with what's going on here on Earth? What are you going to see? You're going to see just the opposite. Our time is going to speed up relative to you. Within 1 single second of your lifetime, you're going to see an hour of our lives, and a day of our lives, and a year, 100 years, 1,000 years, 1,000,000 years, and so forth. So the opposite is going to happen. Our time is going to speed up quite a bit. All right, so special relativity, got 4 conclusions. Conclusion number 1, nothing with mass can travel at the light speed or faster. Einstein said nothing travels at or faster than light speed. That's the only one that required a correction. Nothing with mass can travel at the light speed or faster. Time dilates or slows down in the reference frame, moving near the light speed at relativistic speeds. Space can contract only outside of your reference frame in the direction of motion near the light speed. And mass is a form of energy. So mass is a form of energy. So these are the conclusions of the theory.
But at the start, this was a chance at something new for the city of Seville.